Hello everybody, welcome to another CNCM member lecture. My name is Kelin. Today's lecture is going to be on multiplicative functions. So, this has been a relatively niche topic, historically speaking, in math contests. So until very recently, they have only seen use in a few selected math Olympiad problems, but we have seen an increase in its usage in computational contests in the past year. So even though it's still a lot rarer than other more common types of number theory problems, I figured out that it would be good to record a lecture based on it. Alright, so let's get into a few definitions. An arithmetic function is a function from the set of positive integers to a set of complex numbers. So I'm sure that you are familiar with the basic definition of a function. So for each positive integer input, the function will return a complex number output. A multiplicative function is an arithmetic function f such that for any two positive integers m and n that are relatedly prime, we have f of m times n is equal to f of m times f of n. The product of two multiplicative functions is also multiplicative. It might seem like a very trivial fact, but it can come in handy sometimes. A multiplicative function is completely multiplicative if for any two positive integers m and n that are not necessarily relatively prime, we have f of n times n is equal to f of m times f of n. Oh, and also here's probably the key to this lecture. When working with multiplicative functions, we can split f of n is equal to f of p1 to the e1 times f of p2 to the e2 times f of p3 to the e3 and so on, for each prime power p1 to the e1, p2 to the e2, and so on, dividing n. This is the main idea of many contest problems that involve multiplicative functions. Right, so here are a few exemplar functions. Which of the following are multiplicative? And which of the following are completely multiplicative? So, if you want to try them out for yourselves and avoid getting spoiled, you can pause the video right here. Alright, we'll proceed with the lecture. All of them are multiplicative. So, f of n is equal to 1 and f of n is equal to n to the 7. Both of them are completely multiplicative. In fact, f of n is equal to n to the c for any complex number c is completely multiplicative because of the definition of exponents. The last four are all multiplicative. This should be fairly straightforward if you know the explicit formulas for each of them, so skip the details. Alright, so here's another concept. That's a very important concept in higher number theory, and it should be good to at least know the basics of it for math contests. So the Dirichlet convolution of two arithmetic functions is as follows. The Dirichlet convolution of f of g is equal to the sum over all divisors of n of f of d times g of n over d, which is also equal to the sum of f of a times g of b over all a and b, such as a times b is equal to n. Some basic properties of the Dirichlet convolution are that it is commutative, associative, and distributes over addition. Its most important property for purpose of this lecture is that the Dirichlet convolution of two multiplicative functions is also multiplicative. The proof will be left with the exercise, and as a hint, the last two summations are both very useful. So here's an example of the Dirichlet convolution. Pi times the convolution of pi and 1 is equal to what? So this is, in more conventional mathematical terms, the sum over all divisors of n of phi of d times 1, or the total of d times 1 is equal to what? Alright, again, if you want to figure it out for yourself, you can pause the video right here. Alright, so here's actually a really beautiful proof of this that involves nothing but basic arithmetics. So notice how each of the functions simplify. There are 5 of 20 fractions left with the denominator 20, 5 of 10 fractions left with the denominator 10, and so on. So we get that the sum is equal to n. Alright, so here how you can solve a few contest problems with the property of multiplicative functions. So here's an example from the most recent AIMC 12A. This is the last problem. So let d of n denote the number of positive integers that divide n, including 1 and n. So, and let f of n equals to d of n over the cube root of n. There is a unique positive integer n. Uppercase n, I guess, such that f uppercase n is greater than f of n. For any positive integers n that is not equal to uppercase n, what's the sum of digits of uppercase n? So we can immediately see that d is multiplicative because d of n is multiplicative, and 1 over the cube root of n is obviously also multiplicative. So we can just find individual prime powers e1 and e2 and so on, such that e1 plus 1 over 2 to e1 over 3, e2 plus 1 over 3 to e2 over 3, and so on, are each maximized and take n as the product of 2 to e1, 3 to e2, and so on. Anyway, so here's a pretty cheesy finish that does not require computing out every prime power. So after some calculations, we can find that e1 is equal to 3 and e2 is equal to 2. To solve the problem immediately, since it has to be a multiple of 9, so its sum of digits is also a multiple of 9. So the only choice we have is E. Alright, let's proceed to the next problem. And here's one of the last problems of the most recent AIME. For any positive integer a, sigma of a denote the sum of positive integer divisors of a. Let n be at least positive integer such that the sigma of a to n minus 1 is a multiple of 2021 for all positive integers a. Find the sum of the prime factors near prime factorization of a. So immediately we can see right here that the sigma function is multiplicative, so it suffices to compute sigma of p to m to n equals p to m times n plus 1 minus 1 over p to m minus 1 for each individual prime p, and an arbitrary power m. We can divide this into 3 cases. So the first case is that p to m is not equivalent to 0 or 1 mod 43 or 47. So we can use Fermat's theorem to get that p to a 42m plus 1 is equivalent to p mod 43, and p to a 46m plus 1 is equivalent to p mod 47. And therefore we need n to be a multiple of the least common multiple of 42 and 46. The second case is that p to m is equivalent to 1 mod 43 or 47. So we can expand the fraction that we get at the beginning into 1 plus p to m plus p to 2m and so on, plus p to m minus n. So setting each term equivalent to 1 mod 43 or 47 will give that n is a multiple of 43 and 47. So alright, so the third case is p is equal to 43 or 47. Then the fraction will already be equivalent to -1 over -1, which is 1 mod 43 or 47. So after going through all 3 cases, we can compute the answer as the sum of prime divisors of the least common multiple of 46 and 42 times 43 times 47, and that is equal to 125. Alright, here's the last problem for the most recent HMMT Spring. So let n be a product of the first 10 primes, and let s be equal to the sum over x times y is the factor of n of the totient of x times y. So compute s over n. Anyway, so we can fix x, and notice that the sum of y over y, divisor of n over x is equal to sigma of n over x, where the sigma adapts the definition from the previous problem. So the sum can be written as the sum of pi of x times sigma of n over x over all x that's a factor of n. We can immediately note that that's a Dirichlet convolution of 2 multiplicative functions. So we can just compute this value for each individual prime p. That's equal to p minus 1 plus p plus 1 over p is equal to 2. So we can multiply all 10 prime numbers together to get an answer of 1024. Alright, that's it for today's members lecture. Thank you for watching. I'll see you next time. Bye.